Alright, so here we go with section 1.7. Sorry, I messed something up and I had to start again, so that's why you see this already highlighted. So you're going to hear this word, these words, linear independence a lot, or when vectors are linearly independent. So here we go. So when you have homogeneous equations, you can study them, writing them as vector equations. So remember, homogeneous equations or homogeneous equations are when you have your system of equations, but they're all equal to 0. And so, you know, this can be kind of expanded out to here. All right. So when you have a set of vectors that are said to be linearly independent, what that would mean, so your vector here, 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 when this equation has only the trivial solution. So when this only has a trivial solution, meaning the only way to make this all add and multiply to 0 is to actually plug in 0, 0, 0 right here. Okay? So if that's the only time that you can get this equation to be true, then you know that these vectors that created this system of equations are linearly independent. Okay? And if not, if there exists another answer or different weights, then they are linearly dependent. All right, so let's look at these examples down here. And so I think it's easier to see, like if I look at example 2 first. In example 2 right here, you can kind of tell that if you take this guy and multiply it by 3, you'll get that guy. So I could make up an equation that says, like, call this like vector 1 and vector 2. I can make up a problem that says 3 times vector 1 plus vector 2 is going to equal 0, right? And so right there, that tells me that this 3, and then there's a 1 right here, that 3 and that 1 are not all 0, like the definition says. And so I can't do it. So if I set it up as a matrix, I would put 1, -3, -3, 9. And you can go ahead and augment it with 0 if you want to, but you know, the zeros don't change. If you row reduce this thing, it comes out to 1, -3, and zeros, all zeros here. All right, and so right there means that there's infinite solutions, right? So infinite solutions, therefore this is linearly dependent, right? So there's not only zeros as an answer, there's infinite solutions here. So if I go over here, and you can kind of see, like, this is like upside down, but you see how there's pivots in each spot. That's kind of a good clue, kind of like we said before in the last section, when there's a pivot in each column, this spans R3, that type of thing. And so if you go ahead and row reduce this, it comes out to 1, 0, 0, and put our zeros on the side. And you know, put this in as a matrix with zeros on the side. And then it comes out to 0, 1, 0, and 0, 0, 1. Well, this has one solution, 0, 0, 0, right? And so only the trivial solution exists. So therefore, they are linearly independent. Okay? And also you can kind of see that they're not multiples of each other. Like, you can't multiply this column by like 5 and get this answer over here, or multiply, you know, 2 times -4 is -8, but 0 times -4 is not 5. Like, they're not multiples of each other. That's the easiest way to tell. Okay. All right. So linear independence of columns. So this is what I was just talking about just at the end right there. So the columns are linearly independent if and only if the equation ax equals 0 has only the trivial solution, which is what we just saw there. Let's see, in examples 3 and 4, determine if the columns form a linearly independent set. Justify your answer. All right, so I do have the answers here to save us a little bit of time here. So this right here, you see there's kind of like an extra row that's not really needed in a way, but when you row reduce this right here, look what happens. And so imagine if there were zeros here. We do have the same thing, same situation as we did in example 1, and so these columns are linearly independent. Okay, because the only solution to this is 0, 0, 0. All right, on example 4, so again, you can imagine your zeros there, and so when you row reduce this guy, and you know, it's kind of suspicious because we do have 4. Oops, not 4. I x1, x2, x3, x4. You have 4 variables, and so only having 3 equations, that's kind of suspicious there, and you can go ahead and add up your 0, 0. So really the only hope here, I think, is to have infinite solutions. And so when you do this, you do see you have a free variable. So what that means is that these columns, like one of them was a multiple of the other, and so these are linearly dependent. Okay. All right. Okay, and so in example 5, it says for what values of h is v3 in the span of v1 and v2. So for this question, it's not really, our linearly dependent question is down here. So this is kind of like an old question. All right, so we would have to, for this guy, set up a matrix, 1, -5, -3. I want v3 separated, so 2, -9, and h, and -2, 10, and 6. So here we go, trying to get rid of these two right here, see what happens. So I'm going to multiply 3 times row 1 and add it to row 3. I am going to multiply 5 times row 1 and add it to row 2 right here. So what that's going to produce for me, and the only one that's going to be kind of annoying is this over here. My 1, -2, 2 is going to stay. It produces 0, 0, 1, and 0, 0, and 6 plus h. So right there, there's no solution, right? So for what values of h is this a multiple, a linear combination of those? It's not, so never. All right. If this had come out to 0, I would have said, well, 6 plus h has to equal 0, but this right here means no solution, ever. Like, there's nothing I can do with h. All right, so for what values of h is, are these things linearly dependent? So we can take that same answer that we got right there, because I was row reducing it, so I can just pretend that this line wasn't here, because now we're grouping them all together. So let's take a look at that. So 1, -2, 2, 0, 0, 1, 0, 0, 6 plus h. So let's see. For what values of h is this thing linearly dependent? So if this was going to be true, I can actually have h be anything. I can use this 1 right here and multiply and add to get rid of anything down here. So actually h can be anything, because these two rows match, and I can put anything here for h, like let's say I put a 12 and I get 18 or something. Well, I can multiply -18 times row 2 and add it to the last one to get rid of it. So h can be anything, but also more importantly is that when you look at this thing, if this was going to be your, a system of equations with all zeros here, a homogeneous system of equations, then this right here, because you have this column with no pivot, this guy right there, that means that this system of equations is has a free variable. So there are infinite solutions. I don't even need to consider h really, okay, because v2 is free. All right, so some special cases here. So sometimes you can determine linear independence with the minimal effort. So a set containing only one vector is linearly independent, because like how can you, like there's nothing, you're independent, it's by itself, like there's nothing to compare it to. All right, and let's see, as long as that vector is not just all equal to 0, because anything to multiply to 0. All right. So when you have two vectors, a set of two vectors is linearly dependent if one of the vectors is a multiple of the other. Okay, so you're not going to see situation 1 a whole lot, but this is kind of an important thing. So we got linearly dependent if one vector is a multiple of the other, or in a set of more than two vectors, if any of the vectors, any pair, is a multiple of the other. Okay. So the set is linearly independent if and only if neither of the vectors is multiples of each other. Okay? So for example, like looking at these two down here, if you look at the sets together, like we're trying to look at these two together and these two together. So you see if you multiply this by 2, multiply that by 2, these are linearly dependent. U1 and U2, they're multiples of each other, so they're linearly dependent. And if you put them in a matrix and reduce them, you would see that too. All right, and this guy here, you know, 2 times 1 is 2, 1 times 3 is 3, so it wasn't the same thing. I couldn't do the same, they're not multiples of each other. So V1 and V2, those are linearly independent. All right, so if you were to place linearly dependent vectors, if you were to draw them, like you see 2, 1, over 2 up 1, that's this guy right here, that's U1. And then 4, 2, see how they lie on the same line. All right, they're just like multiples of each other. Like they're both vectors going the same direction, and one's just longer than the other. Like their magnitudes are longer, because this one would be U2. But V1 and V2, they go totally different directions. Okay. All right. Let's see. All right, an index set of vectors of 2 or more vectors is linearly dependent if and only if one of the vectors is a linear combination of the other, so like a multiple or some kind of multiple addition, linear combination. All right, so this is just kind of expanding to more than 2 vectors. All right, so if any one of them is a multiple of the other, it's ruined. All right, so let's take a look at the last part here. All right, so Theorem 7 does not say that every vector in a linearly dependent set is a linear combination of the preceding ones. So for example, like 2 times -3 is -6, and -5 times -3 is 15. So these two right here, they ruin the whole thing. So it's not like 10(7) has to be a multiple of 2 -5 as well. These two, because they're all grouped together, these two being combinations of each other ruin the whole set. Okay? All right, let's see. All right, so if there are, how did I want to finish this sentence here? So if a set contains more vectors than there are entries in each vector, okay, so it has more columns than it does rows, all right, then the set is going to be linearly dependent, all right. And so that's, like I said, there's not enough equations matching the number of variables that you have, all right. So in other words, if there are more columns than rows, you will always have linear dependence because there are going to be infinite solutions to that homogeneous system. Okay, all right. Theorem 8 does not says nothing about the case when the number of vectors in the set does not exceed the number of entries in each vector. Okay. All right. Theorem 9. If you have a set of vectors in a real number system there, if they contain the 0 vector, then the set is linearly dependent because you can always multiply a vector by 0 to get the 0 vector. So having the 0 vector in your set ruins it. All right, so let's check that out. So that rule right here we just went over is right there. So these are linearly dependent. This right here makes it automatic. I can multiply, like 0, 0, 0 is a multiple of everything because I can be like, oh hey, let's multiply this guy by 0, and there I go. Okay, all right. So let's go ahead and inspect these a little bit. So let me see, 4 times 1.5 makes 6. -2 times 1.5 makes -3. 6 times 1.5 makes 9. So what we just discovered right there is that vector 1 times 1.5, or 3/2, makes vector 2. They are multiples of each other, so linearly dependent. Right. This guy right here, if I set this up, remember this rule right there. If I set that up, it has more vectors or more columns than it does rows. So it's automatically going to be linearly dependent. All right, and this is kind of my other situation, but we can look and see here. You could put this in a matrix and row reduce it just to see. But if I try to, think to myself, 2 times -4 is -8. -3 times -4 is 12. But -1 times -4 should be +4. So that right there ruined the pattern that the other ones were having. So this one's linearly independent. These are not multiples of each other. Okay. So why did I put DD? I meant to put LD. Sorry. Okay. That's it. So your homework should be pretty simple, but you're going to do this bookwork in class. So remember, tonight you're just responsible for watching this video and doing section 1.6, which hopefully you did in class. All right, bye-bye.